Hi, I'm Darren Llewellyn. Welcome to another episode of MyToolboxTV. Today we're going to talk about the fundamentals of electricity. And to do that, we got to start with atoms. Let's take a look. This is an atom. An atom is made up of a nucleus. The nucleus has in it protons and neutrons. Now, I'm not a physicist, and I can prove it, and I'm not going to try to be one today, and this is a very simple look at atoms, and this is all theoretical anyway, but a neutron does not have a charge. It's neither positive or negative. A proton has a positive charge. Proton has a positive charge. Now, circling around this atom is an electron. Electrons have a negative charge. Opposites attract in nature. Opposites attract. So that's what holds the atom together. That's what holds this whiteboard together. That's what holds this pen together. That's what holds me together. And so opposites attract. Now, every type of element in the universe has a different number of electrons, protons, and what have you. I'm not going to get into any of that, but this electron, they're orbiting around, however many of them there are, around the nucleus. Protons being positive, electron being negative, that's what holds it together. Now, let's take a look at what happens when this atom loses an electron. When it loses an electron, it changes the charge of the entire atom. Okay? Changes the entire atom. Some atoms have what are known as free electrons. Free electrons, those are electrons that are able to move from one atom to another. Copper, for instance, aluminum, have free electrons. That makes them good conductors. Atoms that have free electrons are conductors. Let's take a look at what happens if you've got a bunch of atoms together, say in a conductor, and what happens with their charges when you apply certain things to them. Now, what if you take several atoms, like say in a conductor, and they're all in a row or grouped together, and each one of these is an individual atom with the nucleus and the electron. Now, let's say that you applied something to this conductor that made these electrons move. Let's say this happened. This electron moved from here and went to this one. And this electron moved from here and went to this one. And the same thing is happening down here. All these electrons are moving. And as these move over, this one, way over here, would then move to this atom. So they keep moving. This one goes here. This one goes here. This one would go to here. This one goes there. This one goes there. This one might go there. That one might go there. Just like that. Before you know it, we've got a flow of electrons. The flow of electrons is current. That's current. Now, what might make these electrons move? That is voltage. Okay? If you apply voltage to this string of atoms, this conductor, that voltage, let's say this voltage, to keep it simple, comes from a battery. If you hook a battery up to this long string, the negative electrons will be attracted to that positive terminal on the battery, and they'll start moving. Okay? That's current flow. So it takes voltage to create current. Current is the moving part of electricity. Current is the moving part of electricity. Voltage doesn't move. You can never say things like, I got 120 volts running through this wire. You don't. You might say, I have 120 volts applied to a circuit, to a load or something, but voltage doesn't move. Current moves. Current is the moving part of electricity. The voltage in a battery, the way that voltage is there, it's a difference. On a battery, you've got separate plates. And when you charge that battery up, you're simply stacking electrons on one side and taking them away from the other side. Let's take a closer look at batteries. This is just a picture of a typical, what might be a car battery or something. Inside the battery, connected to the terminals, are going to be plates. Okay? Batteries could have any number of plates. And between the plates is something called a dielectric. It insulates the plates from each other. Now, inside this battery, if you were to have, let's say, the plates that make up this terminal over here, had the same number of electrons on them as you had on the battery plate that makes connected to this terminal, if they've got the same number of electrons, the battery is dead. In order for a battery to work, it has to be unbalanced. A perfectly balanced battery is dead. Okay? Now let's say we put this on a battery charger. We charge the battery up. What we're going to be doing is moving a bunch, or maybe almost all of the electrons from this side over here to this side. So we've got lots and lots of electrons over here. Virtually none over here. Electrons, if you remember, are negatively charged. So that means that this side of the battery is very negative, and this side is very positive. That makes this the positive battery terminal, and this the negative battery terminal. Remember when I said earlier that opposites attract? Opposites attract. These electrons really want to get over to these positive atoms and vice versa. If you were to take a wire, a conductor, and connect these two terminals together, what you would see is these electrons flowing through this conductor to get back to the positive side of the battery, and once they all got back over there, a good half of them, the battery's dead. Now, if you were to take and put, say, a light bulb in here, as those electrons went through the light bulb, due to something we call resistance, which we'll talk about shortly, this light bulb would light up. So you're actually getting work out of this battery becoming discharged. So you have to have an unbalanced battery that gives you a potential difference. A potential difference. And that is voltage. If there's a potential difference, you have voltage. And that's how we put it to work. We're actually letting those electrons go back home where they came from because opposites attract, and that causes current. So we have current flowing through the conductor. We have that current causing this light bulb to heat up because the light bulb has resistance, and that gives off light, which is what we were wanting. So we can actually get work out of electric circuit. The work we call power. Let's take a closer look at resistance. All right, let's talk about a simple circuit. We just looked at a battery and atoms and those things, but let's look at some of this stuff in a circuit. This is a battery, a single cell battery, negative and positive, a switch, and a resistance, a resistor. We'll get to that in a minute. Let's say this battery's charged up, and from earlier you remember that when a battery's charged up, it's simply the fact that one side of the battery has a surplus of negative electrons, while the opposite side is missing a bunch. So it makes this side very positive. The atoms over here are missing electrons, so they're very positive. Now, when you complete the circuit, and this is a switch right here, when you close that switch and complete the circuit, now current will flow because the battery wants to balance itself. A charged up battery is an unbalanced battery. So it wants to balance itself, and when you complete the circuit, it will do so. It will flow through here, back to this side. When all the electrons get to be balanced on each side, when you got the same number of electrons over here as you had over here, the battery's dead and it stops flowing. Okay? This potential difference in the battery is voltage. That's voltage. Okay? Now, when you complete the circuit, you allow current to flow. So these electrons traveling back, that's current. Oops. That's current. Now, the resistor over here, resistance is opposition to current flow. When you're opposing current with the resistor, something cool happens. Heat is created. When these electrons flow through the resistor, they get kind of mad about it. As they go through there, the resistor is opposing them and they create heat. So basically, they are converting electrical energy into thermal energy. And we have a name for that. We say that's power. That energy conversion there is the power consumption of the circuit. So the battery has voltage because there's a potential difference. The complete circuit allows current to flow. The resistor resists current flow. When it does that, it creates heat, and that's the work that this particular circuit's doing, and we measure that in power. Okay? In just a second, let's take a look at each one of these individual fundamentals that we've learned so far: voltage, current, resistance, and power. So, we've talked about a lot of things today, but we have current, voltage, resistance, and power. Current, remember, is measured in amps. Now, when you see current drawn on a lot of electrical drawings, when you see it represented in Ohm's law, they use the letter I. Okay? And that comes from way back ago when they used to call current intensity. And so that was the letter I. Voltage in Ohm's law, you'll see written as E. And of course, voltage is measured in volts. Resistance is measured in ohms, which a lot of people have heard. And the letter for that is the Greek letter omega, when you see that represented in Ohm's law on a lot of drawings and on multimeters and things like that. Also, sometimes you'll see it just as represented as an R. Power is measured in watts. Okay? And remember, that's the work a circuit is doing. In Ohm's law, you'll see that written generally as a P. So the fundamentals are very important, and you have to have a grasp of them if you're going to learn electrical work. No matter if you're going to be an electrician or electronics person, an engineer or a cable TV person, you have to have a knowledge of these things. Remember that current is the moving part of electricity. Current measured in amps, that's current flow, that's electron flow. Voltage is the pressure. Voltage doesn't move. Voltage is the potential difference applied to a device or a circuit. Resistance, measured in ohms, is opposition to current. When voltage causes current to flow through resistance, we have a conversion of energy from, in the circuit example we used, from electrical energy to thermal, and that's power, measured in watts. And you've got to know these fundamentals. So current's the flow, voltage is the pressure, the potential difference, resistance is the opposition, power is the work that we're going to be doing. Without a full understanding of the fundamentals, it's kind of like being a football player and not knowing how to block or tackle, or a basketball player not knowing how to dribble the ball. Those are fundamentals you got to have to be a football player or a basketball player. Same thing applies for any kind of job that you would have in electrical work. You have to understand what these fundamentals mean. Thanks for joining us today for another episode of MyToolboxTV. Hopefully you increased your knowledge of the fundamentals of electricity a little bit. Very important to know these things. Stay tuned. We're going to have more episodes on the fundamentals. Until then, see you next time.